Welcome to the Ugly Christmas Sweater edition of Notes. This is my take on Chapter 11 in the Brown et al. Chemistry book we have been using, but it's a really great review of intermolecular forces and how intermolecular forces affect liquid properties. So what is an intermolecular force? Just as the name implies, these are the forces that are in between molecules. So picture a water molecule and another water molecule. How do those two molecules interact? That's what we're looking at here. So how does this compare among gases, liquids, and solids? And if you want to pause the video and read through all of this, you can. I believe it's probably in your book as well. But it goes over the definitions between gases, liquids, and solids. And a lot of students struggle with this idea. Well, just think about a gas. A gas has volume, and it's going to take the shape of whatever container you shove it in. And it's going to expand to fill the container. Imagine you've got a bottle, like a 2-liter bottle with a cap. You put gas in there, it's not going to just sit at the bottom. It's going to fill that whole container. And gas is compressible. Fill up a balloon, squeeze it. You can squeeze gas. It flows readily, and it's going to diffuse very, very rapidly. Liquids, a little different. They are going to take on the shape of the container, at least where you find it. So imagine you've got some really weird-looking vase, and you've got water down here. Well, it's going to take the shape of that part of the container, but not the rest of it, because it's not up there. You're not going to pour water into a bottle, and then it's going to suddenly expand through the whole bottle. Water doesn't behave that way. So it doesn't expand to fill the whole container. You really can't compress it. Just put some water in your hand and try and compress it. It's not going to happen. But liquids do flow readily. Just picture any creek or river you can think of. And it does diffuse within a liquid, but it occurs slowly. So pour yourself some coffee, add a little bit of cream, and just watch it diffuse. Now, solids, they have their own shape and volume. You put an ice cube into a flask, it's not going to take the shape of the container. It's not going to spread out to fill the container. That would be weird. And they're pretty much not compressible. Go ahead, put that ice cube in your hand, squeeze it. Or better yet, the table in front of you. Can you squeeze that table? No, you can't. I mean, I'm sure you probably could. We just don't have the equipment to do so. Solids don't flow. And diffusion within a solid does occur, but it's very, very slow. So let's take a moment to compare intermolecular forces to intramolecular. Well, the inter are between molecules. Think about an interstate. It connects state to state to state, so it's in between the states. The stronger your intermolecular forces, the higher the melting and boiling points. And if you think about it, it makes sense. If you have this molecule and they are really attracted to each other, isn't it going to take a lot of energy to break them apart? So it's going to take a lot of energy to break them apart, which means it's going to have a higher boiling point. And what are intermolecular forces? They're just electrostatic forces between molecules. In other words, positives and negatives attracting. That's what's going on. Sometimes repelling, typically just the attraction. These are obviously weaker than ionic bonds, which also have positive-negative attraction. And that's because these are really small charges compared to ionic charges. And the distance between the molecules are much farther apart as compared to, say, sodium and a chlorine atom bonded together. Intramolecular are within a molecule. An intra-highway is a highway that's only in your state. So an intramolecular force is what is holding an actual molecule together, like ionic, covalent, and metallic bonds. Obviously, these are much, much, much stronger than intermolecular forces. And you can see in that little category down there, we've got 3 chemical bonds: ionic, covalent, metallic, and intermolecular forces, and we'll talk about these: dispersion forces, dipole-dipole, and hydrogen bonding. And a lot of times we lump the first 2 together and just call them the van der Waals forces. So let's look at the first one, dispersion forces, also known as London dispersion forces. Let's first go ahead and go with the definition. It's kind of wordy. This is an instantaneous or momentary temporary dipole on one atom induces an instantaneous dipole moment on an adjacent atom, causing the atoms to be attracted in atoms or molecules that are nonpolar. Let me give you an example. Consider a fluorine molecule. You have an F, and they're attached. Now you know they are sharing electrons equally. This is a nonpolar molecule. Total, complete, equal sharing of the electrons. But is it possible at a split moment in time there's more electrons around this fluorine than that one? Which means this fluorine would be negative and this one would be positive. Now imagine that happens in another fluorine molecule. One end is positive and one end is negative. So wouldn't the positive end of that molecule be attracted to the negative end of this molecule? Yeah, that's what we're talking about here, okay? And these occur in every interaction. So any question that you have that says, what kind of forces would you find between these molecules? You're always going to say dispersion. But this particularly happens in nonpolar molecules. So when do they occur? They occur when molecules are very close together. Again, they occur between all molecules. What affects the strength of dispersion forces? This is something called polarizability. And this is where the charge distribution can cause an instantaneous dipole. It's what I explained a little bit ago, where the charge becomes polarized. One more electrons over here than over here, and so on. This increases as the number of electrons in an atom or molecule increases. So then this also increases with atomic or molecular size. Example, if you look at the noble gas column, obviously at the bottom of the column, they're much bigger atoms. Therefore, they are going to have stronger dispersion forces and higher boiling points because those molecules want to stick together better. And the last thing is that molecular shape can affect dispersion forces. If the molecules can make more contact with nearby molecules, then the dispersion forces increase. So if you have a very long linear molecule like you find in organic chemistry and another long linear molecule, those two molecules have a lot of contact with each other, and that increases the dispersion forces. So larger molecules have stronger dispersion forces. So in dispersion forces, we were talking about any molecule, but particularly nonpolar molecules. Now when we get into dipole forces, we're talking strictly about polar molecules. When polar molecules come in close contact with another one, we say they have a dipole-dipole force. Because think about like HF. F obviously holds the electrons more tightly than H. So F is negative, H is positive. Therefore, another HF molecule also has a positive and a negative end. And if they come near each other, they will align so that the positive, negative ends are attracted to each other. This is very, very effective at holding molecules together when they're really, really close together. And this results in much higher boiling points than dispersion. And that makes sense. If you've got a positive and a negative end that are attractive to each other, it's going to be harder to break them apart. And the difference here is that in dispersion, that's just a temporary positive negative thing. It's not always there. It's some split moment in time. You have more electrons here than over here, and then that shifts and it moves. That's not the case in polar molecules. You always have a positive end and a negative end. So it makes it harder to break them apart, and the boiling points go up. For molecules of approximately equal mass and size, well, how do you know which one's going to have stronger forces? That depends upon increasing polarity. So HF is way more polar than HI. Therefore, they would have stronger forces between them. The dipole-dipole forces do occur with dispersion forces. Again, anytime you have a question, what intermolecular forces are here? Dispersion will always be your answer. And then you have to analyze it and decide if there's more answers besides that. But the molecules will always arrange themselves to maximize attraction and minimize repulsion. So the positive and negative ends are going to line up together. Now for the last intermolecular force, hydrogen bonding. The definition here is that it is an attraction between a hydrogen atom that is attached to a very electronegative atom, usually F, O, or N, and a nearby small electronegative atom in another molecule or chemical group. And a lot of people joke and go, hydrogen bonds are fun, F-O-N, to help you remember the fluorine, oxygen, and nitrogen. So in other words, if you have H bonded to F, O, or N in one molecule, that hydrogen can form a bond with an F, O, or N in another molecule. And the H atom is always bonded to a non-bonding electron pair. So take a look at that picture. On the right, you've got the H attached to the O. And notice it is forming a bond with that electron pair on that oxygen atom. Now, these are special dipole-dipole attractions because, again, you have a region of positive and negative that's always there. And if you think about like H and F, the H is positive, the F is obviously negative, and the F is pulling all those electrons toward it, leaving basically a bare hydrogen nucleus, and it is very positive. So not only does that positive charge attract negative charges, but because that hydrogen is so incredibly small, it can get really, really, really close to that other molecule. So in that picture, that H atom is really close to the O in the water. And this is what results in a very strong bond, much stronger than dispersion and dipole-dipole, but still weaker than a covalent bond that we see within a molecule. So dispersion, dipole-dipole, and hydrogen bonds are our intermolecular forces. There are some other forces going on that don't fall into that category. So let's deal with the first one, the ion-dipole force. This is where ions can be attracted to polar molecules. So think about like a sodium ion. Isn't it attracted to a water molecule, which is polar? Yeah. So cations are obviously attracted to the negative end of a dipole, and the anions would be attracted to a positive end of a dipole. And the strength of that attraction increases as the ionic charge or the magnitude of the dipole moment increases. So if you've got an aluminum ion, there's going to be a stronger attraction than a sodium ion because aluminums are 3+ and sodium is just a 1+. And this is very, very important as to why ionic substances dissolve in polar liquids. We always say like dissolves like. Well, ionic and polar are not like, but they act similarly, and it works. The other kind of force is a dipole-induced dipole interaction. And this can occur between a polar and a non-polar molecule. I know, sounds weird because non-polar doesn't have a charge, right? But this becomes stronger as the magnitude of the dipole of the polar molecule increases and the polarizability of the nonpolar molecule increases. So remember, in nonpolar molecules, even though the electrons are being shared equally, they're constantly moving. And there can be a moment in time where we find more electrons on one side than the other, which causes that momentary dipole, that momentary positive, negative end. And it is going to be attracted then to a polar molecule. But again, probably doesn't happen as often as we see the others. All right, let's do a quick roundup before we move on here with the rest of this PowerPoint. Dispersion forces occur in all substances. The strength increases with increasing molecular weight, and it depends upon the molecular shape. The dipole-dipole forces are in polar molecules, but they have a smaller contribution to the total intermolecular attractions than the dispersion forces. Again, dispersion happens everywhere. So here's a couple of takeaways on the right side of this slide. When the molecules of two substances differ widely in molecular weights, and there's no hydrogen bonding, dispersion forces tend to determine which substance has the stronger intermolecular attractions. When molecules of two substances have comparable molecular weights and shapes, dispersion forces are approximately equal, and then at that point you'd want to address dipole-dipole forces and hydrogen bonding. This is a great flow chart, and if we are still using the Brown et al. Chemistry book, I know it's in there. This is such a great chart for you to walk your way through to try to figure out what kinds of forces you have. So let's start at the top. First, are there ions present? If the answer is no, then you want to ask yourself, well, are there polar molecules present? And if the answer is still no, then you only have dispersion forces. And there are some examples for you. Methane, CH4, and a bromine molecule, Br2. But let's go back up. What if there are polar molecules? Well, Are H atoms bonded to N, O, or F? If the answer is no, you only have dipole-dipole forces. And again, they give you some examples. If there are H atoms bonded to N, O, or F, you have hydrogen bonding. And they give you some examples there. You have ammonia, NH3, and methanol, CH3OH. Go back to the top. What if there are ions present? Are there polar molecules present? If the answer is yes, you probably have an ion-dipole force going on. For example, salt dissolved in water. If there are no polar molecules, then you just have ionic bonding. And there are some examples of ionic bonds. Now, I don't know if you noticed at the bottom of that flow chart, but it says increasing interaction strength. In other words, your dispersion forces are the weakest, ionic bonds are going to be the strongest. So I went ahead and rewrote that down below. Dispersion forces are weaker than dipole-dipole, which are weaker than hydrogen bonds, which are weaker than ion-dipole, which are weaker than ionic bonds. We already defined a liquid early on, so what we really want to do now is get into a few liquid properties and how is it that intermolecular forces cause them. So the first one we want to look at is viscosity, and that is the resistance of a liquid to flow. You could think about syrup. That brown cheap syrup you buy at the grocery store to put on your pancakes flows pretty well, but if you actually buy corn syrup, it flows very, very slowly. That's viscosity. Two ways to determine this. One, you could just time how long it takes a liquid to flow through a vertical tube. And another one is you could literally have two liquids and put a steel ball and time how long it takes to go through that liquid. Molecularly, what is happening? Well, it has to do with how easily the molecules of the liquid can move relative to one another. And this depends upon the attractive forces between the molecules, the shapes and the flexibility of the molecules. If you've got molecules that are sticking together tightly, they're not going to flow over each other, and you're going to have really, really high viscosity. I'm old, and when I was young, we had these great Heinz ketchup commercials. You could probably find one on YouTube. And the guy would go to the top of a tall building and he'd set up the glass bottle just ever so slightly askew, and he'd run down all these stairs, go out there, hold out his hot dog, and then the ketchup would finally pour out onto his hot dog. That is really, really strong viscosity, or really real thick liquid. But for a series of related compounds, viscosity increases as molecular weight does. Now, viscosity is going to decrease with temperature. And that makes sense. If the temperature increases, you're starting to break those attractions between molecules, and it's going to let them flow over each other better. And I always like to think about it in terms of lava. Really, really, really hot lava, it can usually flow pretty well, but as it starts to cool down, it's going to move much more slower. It's going to congeal and become more gel-like. Another liquid property is surface tension. And you've seen it. You've seen the bug on water. How does it do that? If you're really careful, you can get a paper clip to balance on water. Well, surface tension is the energy required to increase the surface area of a liquid by a unit amount. What you need to take away is that the surface molecules are experiencing this net inward force that's pulling the molecules closer together and making that surface be kind of like glass. And that's really all you need to take away from this. Liquids also show capillary action. And you've seen this if you've ever taken your straw in a drink and put your finger on the top and pulled it out. You can see the liquid sticking inside the straw. Well, these are cohesive forces that bind similar molecules together. We know water molecules bind to water molecules. That's cohesion. That's when the same molecule bonds to itself. Well, adhesive forces are where a molecule binds to a different molecule. In this case, water binding to a glass tube. And capillary action is simply the rise of liquids up a narrow tube. Well, how does it work? Adhesive forces occur between the liquid and the glass tube. There are cohesive forces going on between the molecules of the water, surface tension, in other words. But when the adhesive forces are greater than the cohesive forces, the molecule will attach to the glass better than each other, and they will move up the tube. to a point, eventually gravity overcomes that. Now that picture shows you something interesting. If you look at the top of the water in the tube, you see that it looks like a meniscus, like we see in a graduated cylinder. And that is because the water is so strongly attracted to the water or to the glass slides. The other one is mercury. Notice it has a bubble that goes up, and that's because mercury is so much more dense and so much heavier that you have stronger cohesive forces going on. This is going to just be a very quick review to remind you to go and look at these in more detail and just remember things that you should have learned in basic chemistry. Now, this is phase changes. And what are we talking about here? What do we call it when a liquid becomes a gas, or a gas becomes a solid, or a solid becomes a liquid? And there are all those terms in that left-hand diagram. But I want you to think about what temperature is doing to molecules. As the temperature goes up, the molecules start having more and more movement. They start breaking those intermolecular forces, and eventually a solid can become a liquid, and then a liquid can become a gas. You need to know the names of all those processes. You need to know whether or not energy is required or if energy is given off. Obviously, to turn a liquid into a gas, you're going to put energy in. But if you want to take that liquid and cool it down enough to become a solid, you're going to have to remove that. And so we're talking endothermic and exothermic here. Recall that temperature does not change during a phase change. And if you look at the right-hand graph, between B and C, the solid is becoming a liquid, and between D and E, the gas is forming. Well, the entire time that liquid is becoming a gas, the temperature does not change. And you need to know on that graph where exactly are the phase changes. And what do I mean by that? Well, if you look at A, it's a solid. So when you reach B, the solid has reached its melting point. But let's go from the other direction. D to C, we know that's liquid. When the liquid reaches C, that is the freezing point. So depending on which direction you're moving, to the right or to the left of the graph, will depend upon whether or not it's the boiling point or condensation point, freezing point, or melting point. So make sure you go back and review all that. Before we go a little further with what we were just talking about, let's just quickly review critical temperature and pressure. The critical temperature is the highest temperature at which a distinct liquid phase can form. It's the highest temp at which you can have a liquid. Beyond that, you don't have a liquid. The greater the intermolecular forces, the higher the critical temperature. If there's hydrogen bonding, expect really, really high critical temperatures. Critical pressure is the pressure required to bring around liquefaction. There is something called a supercritical fluid, and this is when you exceed the critical temperature and pressure, which you're going to see on the next graph. The liquid and gas phases are indistinguishable from each other, and the substance fills the containers like a gas, but the molecules are closely spaced like a liquid. Okay, I lied. Graph is on the next slide. Let's talk about vapor pressure really fast. A lot of kids struggle with this concept. It's just the pressure exerted by a vapor above a liquid when the liquid and the vapor are in dynamic equilibrium. So just imagine that you've got like a pop bottle and the cap is on. You've got liquid in there. Now, is it possible that some of those molecules on the surface are going to get just enough energy every once in a while and they're going to release and they're going to sit above the liquid? That's vapor pressure. Molecules will naturally evaporate on their own without addition of heat. And depending on how many gas molecules are sitting there above your liquid, that's vapor pressure. So the more those molecules can break free and evaporate on their own without added heat and temperature, then the more vapor pressure you're going to have. But if those molecules are sticking together really well, they're going to remain in the liquid and that vapor pressure will be lower. Now, if you have an open container, equilibrium's never going to be reached because those little gas molecules are just going to float off. And that's just what happens. So vapor pressure and boiling point, the greater the pressure, the higher the boiling point, because it's just keeping all of that in check. All right, here's the other graph. And this is a phase diagram review. It just shows the conditions under which equilibrium exists between two different states of matter. Pay attention to what's happening with your pressure and temperature. Pressures on the y-axis, temperatures on the x. A couple things I want to point out to you. Number one is C, the critical point. That's the point at which above that temperature and pressure, you have a supercritical fluid. You cannot distinguish a gas from a liquid. T is another really cool point. It's called the triple point. It is the point at which at that pressure and that temperature, you will find a solid, liquid, and a gas. And if you Google it or put it on YouTube, you can see a very short video of what this actually looks like. And it's pretty cool. If you have the proper equipment to make that correct temperature and pressure, you can actually see water boiling, freezing, and turning into a gas all at the same time. It's very, very cool. A couple other things to notice. Look at that red line. The red line is the vapor pressure curve of a liquid, and this occurs between a gas and a liquid. And you notice if you move to the right, it's vaporization. If you move to the left, it's condensation. And then if you look at the green line, that is the difference between a solid and a liquid. Nope, I'm sorry, green line. It looks green here. Green line is between a solid and a gas. If you're moving to the right, you have sublimation. Moving in the other direction, you have deposition. So like frost, going from a gas to a solid on your windshield, that would be deposition. The blue line goes between solid and liquid. And again, that is your melting and freezing. By the way, melting point at 1 atmosphere is what we call a normal melting point. And because we're talking about liquids, let's talk about liquid crystals for just a moment. This is that viscous, milky state that some substances have between a liquid and a solid state. It's kind of an intermediate phase between the two. It has some structure of a solid, but it also has the freedom of motion of a liquid. And the purpose of liquid crystals is they are used as pressure and temperature sensors. They're LCDs in watches, TVs, computers. And the reason why they're really useful is because the weak intermolecular forces that hold molecules together in a liquid crystalline phase are easily affected by temperature, pressure, and electric fields. So they can be manipulated for great purposes. And lastly, there's just lots of types of liquid crystals. And this is a picture, if we're still using the Brown et al. Book. You can go in and look on page 468. But basically, these different liquid crystals differ by how the molecules are arranged. You'll notice in some of them they're totally random, and some of them they're lined up in a particular way. But all of these have to meet a certain characteristic, and that is rigid. So we're talking double and triple bonds, benzene rings. These are not ionic due to high melting points. They tend to have a long axis. They have rod-like shapes, and they are polar groups with dipole moments.